Test, test. Right. Welcome back to Physics 112. How are you guys today? Did anyone go to the class on Wednesday? I heard almost all of you. So didn't expect that. So I'm really happy that you came to the class on Wednesday. How did Ross do? It's really good. Oh, okay. I guess it's my fault. I set the expectation probably too high. Next time I lower your expectation. But he's good. His physics is good. All right, so today we will talk about first, any question? We will have exam. So the plan is today we will have lecture 29, lecture 30 on Monday, 2 review sessions, and then exam 4 on the following Monday. I'll be in Utah on that Monday, but you will have exam, and I will follow from a distance in case there is any technical glitch like 2 exams ago. I posted equation sheet. We may cover interference, but today the plan is to cover, well, to finish lenses. And if we have time, we will cover eyes. But learning about human eyes is not a typical topic in introductory physics, but since there are many pre-meds in the lab, we will cover that. And then if we have time, I will do interference and diffraction. So this is the plan. I will still be in Utah on Wednesday, but I can give a Zoom lecture, or if you like Ross can come. And then the last lecture, either it will be review or I will just give a summary of the rest of the textbook, basically. All the fun things about spatial relativity, quantum mechanics, light as duality of light. Light is either particle or wave. I'm happy to do that on Friday, or if you want a review session, I can do a review session. Okay, and then final exam, and then that's it. You don't have to deal with me again for the rest of your life. Okay, so yesterday, Gabe, you have a question? Yeah. Almost class time. Almost, because I don't decide that, the university decide that. I can give you the exact, but it's basically 10 a.m. I think 9:40 a.m. until something. It has been decided, it was decided well before the semester started, okay? So I was really happy also to see a few of you came to the lecture yesterday. So I'm just gonna be fully transparent with you. If you ask me for a letter after the class, I'm gonna be a little bit formulaic. I'm gonna ask you to fill questions. I'm gonna watch your video in the beginning of the class, the video after, in the end of the class, I'm gonna ask you to make video. The goal is so when I write my recommendation letter, I can somewhat personalize it. And then there will be a lot of questions, like where do you sit? Did you go to TJ Haas talk? Did you go to Alex Dunn's talk? Did you go to Kamran's talk? How many times you ask question in the class? Like, if your grade is good, I don't penalize it if you don't ask question in class. But if your grades can be improved, if you don't ask question, then the letter will not be that strong. If you sit at the back, then it may not be as strong. Including people, one person already got an A and he's sitting at the back. But if you want a strong recommendation letter, ask questions. So this is, and then there will be points, right? If you go to TJ's talk yesterday, I give you +1. So next week, a colleague of mine, he is not a president of anything, but he was an HHMI faculty scholar around 2016, Alex Dunn. He and I went to Caltech, and then right now he's a professor at Stanford. He will be giving a talk after the class, basically on Wednesday. Okay? So maybe 2 years from now, when you need my letter or you need one letter, and you're thinking that I would be a good person to write you a letter, then there will be that question. Did you go to Alex talk? If not, why? A good question would be, I have to help my parents, or I had to go to a conference. Just be honest. Okay? I just like to be completely transparent with you. Any question? Any question from people who are sitting at the back? Derek, any question? Okay. All right, so let's have an iClicker question, but I need to set it up. So today we will talk about, I will do my best to finish lens and it will be a miracle if I can finish human eye, but let's finish the lens. So I'm gonna pose a question that is related to the most important concept in ray optics in this class. Not Huygens principle, but Fermat's principle of least time. So imagine that we have a weird shape swimming pool. And you can kind of see that it looks like a lens. So basically it fills with water. And then you want to reach from point A from point A to point B. I still don't know how to relate with you. I'm a little bit older than you, so maybe what Taylor Swift is still the thing. So there is her fan club and Taylor Swift. So the question is which path that takes the least amount of time. So for fun, I'm just gonna do target. Okay. So so I already sent it to my clicker. So the answer could be A, B, and C. So you just need to tap whether the answer is A, B, or C. Okay. No hurries. Take your time. Yeah. And huh? Oh yeah. There are more than 2 answers. Let me put it that way. There is actually infinite answers to this. So 15 more seconds. If you're not sure, just tap the screen. You all will get full credits. Okay. So what is the answer? Let me show you the answer. Your answers, which is good. This is what I want to see. So one thing that I forgot to mention is that the way the pool builder designed the shape of the pool is he is really clever. He designed the pool such that if you run, okay, so first, sorry, I didn't set it up right. Woke up at 2 a.m. This morning. So you, the fan club can run from a parking lot, so can run faster, and then has to swim. Either has to swim or just touch the edge of the swimming pool and run like all the time. So if you go straight, then you can run fast. The total path length is less, but you have to swim, which is slower. So it turns out if you are clever, you can build a swimming pool such that all this path takes the same amount of time. So in a way, this is simulate lenses. So if you want to build a lens that focus, how to do this? Sorry, that focus lights, since light follows or travels along the path that takes the least amount of time. This is how lens work using Fermat principle of least time. Okay. So on the exam, there could be different swimming pools, different shape of swimming pool. Okay, so basically, let's take a step back. So we started lecture, like Monday's lecture, with laws of ray optics, and then there is law of reflection and law of refraction. For reflection, it's basically mirrors. So you have, I think your book use plane mirrors or flat mirrors, and convex. And convex is the one that Ross covered, and I cover concave. And for refraction is basically lenses. And we will only do two types, converging. Some textbook use the term positive lens. Some textbook, what do you call that thing? Even be more specific, they call this concave. But in this class, we use the term converging, and the opposite is diverging. And if we use this kind of terminology, then it's convex. Okay. But the one that we use, the terms that we use, are converging and diverging. So these two are the ones that we will discuss today. And this one example is human eyes, which maybe we will discuss on Monday. Okay, so this one is lens basically only has refraction, which is not true. Lens also reflect lights, but in this class, lens only deals with refraction. Okay. So consequently, I have this iClicker question for you. So on Monday, I asked you that if I submerge a converging mirror, interesting. The term that we use is concave. Concave mirror is immersed in water. The answer to the iClicker question is that its focal length doesn't change. The question is when a converging lens is immersed in the water, initially in air, and then the focal length in air is, let's say, x. Does its focal length increase or decrease in comparison with its value in air? Okay. So you have a lens initially in air, which is, it has the refractive index of 1. And then glass, always the same. The lens is made of glass, so glass doesn't change. But you change the medium, the medium outside the lens from air to water. What happened with its focal length? So it's basically we have uniform distribution. Maybe I need to stop. Let me stop, or maybe let it go. So basically, lens only deals with refraction. That means it depends on the medium. or the refractive indexes of the two media, the plural of medium. Okay. So A shouldn't be the answer. Now the question is whether it increases or decreases. So 5 more seconds. 3, 2, 1. It seems that most of you thinks that the answer is increases. Anyone wants to share why? Yeah. Hernandez, what is it? Oh, Arman. Yeah. Ah, I see. This is why you need to read perusal, or you need to go to this class. You need to go to the lecture. I don't cover all textbooks because your textbook is massive, right? But Arman actually read perusal really carefully. There is a formula that you can use, but using your physics intuition, why it should increase. So maybe this picture helps, maybe not. So the reason why light bends, because there is a different indexes, right? This one can be N1, this two can be N glass or N3, let's say. The smaller the difference, then the less bent the light would like to be. Okay, so initially the difference is between 1.5 and 1. So initially 1 and 1.5. I mean, this is light goes from air, glass to air, and then I don't know, final from water, glass, and water. This is 1.5. So air, glass, air becomes water, glass, water. So the bending of light decreases, and the focal length is how good a lens or an optical component bring lights together. So if the bending is less, then the focal length increases. Does it make sense? That's how I view it. So what did I write? The light is bent less. Okay, good. Any question? So basically, next is converging lens. Converging lens is basically if you have a collimated beam is probably a strange term for you. Basically, collimated beam, you can view it as a parallel beam from a distance. It's a parallel beam. One example is a laser pointer. It's a collimated beam. Light from light bulb is not collimated because it's not parallel, but laser pointer is parallel. If you have a lens, you can focus the light beam into a point. You can also expand it if you want. And if you have a point source, you can make a collimated beam by using converging lens. Okay. There is a principle, the second principle that we discuss in optics. What is the principle that we use to be able to come up with this spatial rays? What is? Yeah, you. Yeah. What is your name? Yes, you. Yeah. Yeah, one of you. Yeah, you. Yeah. Yeah, the one who is smiling. Yeah. 3 of you are smiling. Yeah, Grace. Oh, you're Grace? Okay, good. There is another principle that we discussed earlier in the class. It's principle of reciprocity, I think. So basically, if the path that light takes, if you can come up with a rule or solve the, let's say, Fermat's principle of least time for a system where light goes from left to right, then the same path also applies if you shoot light from right to left. Here, okay. The right to left is different, but basically flipped. This one is flipped by 180 degrees. You get this one, right? So that's the other principle that I haven't emphasized that much. Maybe Ross did. Any question? All right. Next is diverging lens. Diverging lens is literally cause lights to diverge. But for diverging lens, so let me show you I skipped one equation sheet for the exam. So for lenses and mirrors, the equations are fairly simple. We have discussed this. This one over object distance plus 1 over image distance equal to 1 over f, and the magnification. These two equations apply to both mirrors and lenses, whether they are flat, converging or diverging, concave or convex. One thing that is tricky is their signs. Okay, and I'm being nice to you, really. I'm not joking. When I was taking this class 25 years ago or more, I had to memorize I had to understand all of this signs. But I will give you this sheet for your exam. Okay, so for converging lenses, the focal length is positive. Lenses, the focal length is positive for converging lenses, and focal length is negative for diverging lenses. And maybe this is the last time I'm going to ask you this question. So there is this formula here. Do you know how to, if somebody asks you to derive this equation from scratch, what is your starting point? What principle that you would use to derive this equation? This is probably the 10th time I asked this question. Yeah, so you can use Fermat's principle of least time to arrive at this equation, but since we don't have time, we will not do it in class, but I'll be happy to do it with you in office hours. Just give me like 45 minutes. All right, so basically converging lens, the focal length is positive. So what does it mean by positive focal length for lenses? For mirrors, positive focal length, that means the focal length is in front of the mirror. But for lenses, it's the opposite. The positive focal length, that means the focal length or focal points is behind the lens. Okay. And if you think the equation, the table is not good enough, you can ask me to add any sentences here. Okay. But I think that table is the best one on the internet right now. So, and then for diverging lenses, the focal length is negative, so it means the opposite. It means that the focal point is in front of the lens. So if you come with a collimated beam, the light will get refracted and it will leave the lens as if they come from the focal points. Do you get it? This is really important. Okay. I may ask you this question. Okay, this is important because mirrors and lenses are similar and you have convex and concave. So you need to know the difference between all those four. And the difference mathematically is easy because I give you the table, but it's good if you understand what you do. So for example, if I give you a lens, or if you inherit a lens, you don't know the focal length, how would you do that? If I give you a lens, yeah, you, what is your name? Finn. Yeah, if I give you a lens, you don't know the focal length, how would you do that? Since you're taking this class, you should know how to do that. You find a lens, let's say, or you buy a lens, you bought a lens 10 years ago, and you don't have the spec sheet of the lens, and you're curious, and you need to know the focal length of the lens. How would you do that? How would you figure out the focal length of a lens? That's a lot of work. You can, but you don't want to make measurement. You don't want to measure the curvature, because when you measure the curvature, you have to touch the lens and you may destroy it. Because if you have lenses, sometimes it's better not to clean your lenses. It's better to keep it a little bit dirty, because when you clean it, you can make it worse. So from this figure, what you do is you just get basically have a piece of paper and put your lens, and then until you see a focus light. Let's say you have a lens here, and you see a focus light here. When you move it closer, the light is defocused or not as focused. So you find the length such that the light is as focused as possible. Then the focal length is this distance. I still use this. People still do that. That's how we measure or guess the focal length, right? Any question? Next, there is simulation online that you can play with. And I cannot recommend this simulation enough. I wish I had it when I was your age, 25 years ago. Actually, 30 years. Okay. So this is nice, but again, don't take the terms, meaning we use slightly different terms. Instead of concave and convex, we use converging and diverging. So basically, you can change the focus. You can even change it from positive to negative. So there is this is negative, right? So it's concave right now. I see. Interesting. I apologize, because I don't use this term. So this one is actually convex. So I'm really sorry for that. Yeah, so you can change the focal length, and you can change the image distance. And then let's say if your object distance is here, the image will be behind the lens. So behind the lens, that means the image is real or virtual. For lens, it's 50-50. It's really good. But for mirrors, real image is in front of the mirror. For lens, it's the opposite. So here, the object distance is positive, but the magnification is positive or negative. The magnification is negative because the image is inverted. It's real and inverted, and it's slightly smaller. Okay. So I encourage you to play with this so you can make the image virtual, which is in front of the lens instead of behind the lens. We can make the image smaller, bigger, upright, inverted by changing the distance. Okay. All right. So this is how I teach mirror and lenses, which is slightly different than how Ross did it, I think. So I try to emphasize, oh, sorry. I try to give you, so there is this blank canvas if you want to test yourself that you can print. But right now what we are working on is what we're discussing right now, the principal rays of mirrors and lenses. So there are two types of mirrors or three types of mirrors. The first one is omitted here. Concave and convex, two types of lenses, converging and diverging. These are the terms that we use. If light travels parallel from the principal axis, for a concave mirror, then light will bounce and hit the focal points. You guys know this. Yeah, Sophia. Yeah, it's for mirror is so this is converging. For mirror is different. Yes, you focus lights using a concave mirror. So the mirror is curved inward, or you can crawl into a cave. That's one thing to remember. So anyone remembers, or did Ross go through this? Why the lights hits the focal point? What is the law here? The law that we use is reflections, which is angle of incidence is equal to angle of reflection. So all of this obey, or the ones on the top row obeys that law. So this angle here, sorry, what? Apparently doesn't work. So this is the normal. So this theta of incidence equal to theta of reflection. Similarly here, okay, normal because the mirror is circular or spherical, then the normal is from C. And again, angle of incidence is equal to angle of reflection. Maybe I shouldn't repeat this. Maybe Ross did it this way. But for lenses, if you come with a parallel light or collimated beam, it gets focused to the focal points behind the lens. For a diverging lens, it gets diverged, bends away as if it comes from the focal point, which in this case, in front of the lens. Okay. So that's one. And using principle of reciprocity, you can come up with a different rule. Let's say light comes and hit the focal point, then it will bounce and deflect it, and the deflected beam or reflected beam will be parallel with respect to the principal axis. And similarly for convex mirror, if light is directed towards the focal plane, which is behind the mirror, not lenses, then it will be reflected parallel from the axis. I think I draw it here. So if the light hits the focal point, the reflected beam is parallel with respect to the principal axis. Similarly here, if it approaches the focal point, the reflected beam is parallel with respect to axis. For lenses, if light hits the focal point, it will be refracted. The transmitted light will be parallel with respect to the axis. And similarly, if the light is pointed towards the focal plane, there are two focal points, not plane, focal points. Then the transmitted light will be parallel with respect to the principal axis. Fabian, is that clear? Because there will not be a principal rays cheat sheet on the exam. Because otherwise, there is nothing to test, right? Like otherwise I would just test you, can you find the information on the cheat sheet? So historically, exam 4 is when students make up their grades. So if you think that exam 4 is more difficult than exam 3, typically that's not the case. I don't want to hear you claim that. Sorry. lack of sleep. Sometimes I get cranky when I don't have enough sleep. Okay. Next, I think your books have 4 or 3 principal rays. I don't remember exactly, but from the picture that I got, it only covered 3. Actually, there is another one. So I decided to only cover 3. Here, if the light hits the vertex, the name of this point is vertex point, then because the normal line is looks like this, then the angle of incidence is equal to the angle of reflection, then it will be deflected symmetrically. And similarly for a convex mirror, because the normal line also is perfectly horizontal, then the angle of incidence is equal to angle of reflection. For lenses, if it hits the vertex point, the light doesn't get altered by the lenses, either by converging lens or diverging lenses. So this is something that you kind of have to memorize, I think. Because the rest of that, either you follow reflection, law of refraction or law of reflection. Okay. And I think this is just all of them combined, all the principal rays combined. And this one is taken straight from perusal. Basically, the light can come either parallel. Okay, first, basically light from an object can be reflected to all directions, not only to 3 directions, but there are 3 special principal rays, or there are 3 principal rays. And the position of the image is the intersection of 2 or more of the rays. Once 2 spatial rays intersect, the rest will intersect. So you can just memorize 2, and then you'll be set, or you don't have to memorize all of them. And you can find the image by finding the intersection of 2 spatial rays, similar to this one. When 2 rays intersect, then you get the image. And on the exam, I may ask you to draw the principal rays, take a picture, and upload it. And we'll grade it manually. Okay. And similar to what Ross covered, you can put the image behind the focal point, exactly at the focal point, closer to the focal point. And by using 2 or more, in this case, your textbook used the first and the second in all of them. And in some of them, your textbooks use all 3. You can figure out where the object is. Okay. Good? Yeah, Malika. Sorry. Thank you. Is that your question or no? Please continue. Yeah. Good. So real for lenses is when real is when the image is behind a lens. It's the definition for a real image is if you put your iPhone, you can capture the image. Or in the old days, if we put paper, you can capture the image. So if we have a concave mirror, if you stand at the right position, you can capture the image using paper. But using a flat mirror, you cannot capture the image. Your eyes can see an image, but when you put iPhone behind the mirror at the same distance, you cannot capture anything. So definition of virtual and real, mathematically, if the image distance is positive, in terms of position-wise, for lenses, if the image is behind a lens, then it's real. In front of a lens is virtual. In front of lens is like this condition here. Okay. But here, because the image is behind the lens, then it's a real image, right? And here, virtual. And in your exam, you don't have to draw dot dot dot, but it's a common convention in optics that we use dot 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 for non-real ray extrapolation. If we extrapolate, let's say, this principal rays, then we extend it with dash lines. Yeah. Yeah. And you cannot capture it, so it's not real. It's interesting. So you see, the way we see is, I think, mostly in our brain, not in our eyes. Any question? Okay. Next is for diverging lenses. The focal point, the focal point right now is in front of the mirror. So if light travels parallel to the principal axis, it gets bent, and the direction is as if the light comes from the focal point. And we have discussed the rest of the principal rays for diverging lenses. And this figure is taken straight from your textbook, I think. Any question? Is Gabby here? No? When I first taught this class, I remember all of my students' names. Now I'm getting old, so I think I memorized 1/4 of your names right now. All right, so let's do a little bit math, maybe only one sample problem. Do you want to do iClicker or do you want me to do it for you? iClicker, okay. So the equations is really simple. And I'm going to, okay, so how to do this? All right, so I'm gonna write the condition here. So we have this question. I have this iClicker question for you. It's a converging lens. The reason I'm writing it right now because I want to show the cheat sheet. Converging lens, and I'm being nice to you. I give you the sign. So 1 centimeter. On the exam, I can do like this. So that means I want you to figure out whether the sign is positive or negative. But right now, I remove the absolute sign. An object is placed 3 centimeters before the image. So 3 centimeters. 3 centimeters before, which is in front of the lens. So the sign is positive. The question is, what is the image distance? And you only need to answer the first one. There are 2 questions right there, okay? And then I'm gonna show you. I'm not sure whether this sheet is necessary, but in case it helps. Good. So almost all of you have answered. So 20 more seconds. Change my mind. I don't think that is necessary. All right, 3 more seconds. 2, 1. So the answer is B. Well, I don't know. Let's do it together. So the question is, the equation is always 1 over S. 1 over S prime is equal to 1 over F. And the question is 1 over S prime. No, the question is S prime. 1 over S prime is equal to 1 over S minus 1 over S, 1 over image distance